Welcome. So in this video we'll learn about the concepts of acids and bases. Concepts of acids and bases. So we know that there are three concepts of acids and bases. First one is Arrhenius, second one is Bronsted-Lowry, third is Lewis concept. So Arrhenius concept, as per Arrhenius concept, acid is a substance which gives H plus sign in the aqueous solution. So as per Arrhenius concept, acid is a substance which gives H plus in aqueous solution. And base is a substance which gives OH minus that hydroxyl line in the aqueous solution. So HCl, HNO3 and acetic acid are giving H plus ion in the aqueous solution, so these are the acids, whereas NOH and KOH are giving hydroxyl line in the solution, so these are the bases. So in this all the reactions are irreversible, so there is no mention of reversible reactions. So all these reactions are irreversible. Another point about the Arrhenius concept is that acid when react with base gives the salt and water. So HCl will react with NOH gives the NaCl plus water, HCl plus KOH gives the KCl plus water, and similarly acetic acid plus NOH gives the sodium acetate plus water. So this is the concept of acid and base, that acid and bases when combined they give salt and water. Then another concept is the Bronsted-Lowry concept. As the Bronsted-Lowry concept, acid is a substance which is a proton donor and base is a substance which is proton acceptor. Water, there is no requirement of aqueous solution in this case, no requirement of water. In fact, water can act as acid as well as base. For example, here water is acting as base and it is taking the H plus ion, forming the hydrogen ion. So this is conjugate acid of this base, and we have this acid here. It is acting as acid because it is releasing the H plus ion, giving the H plus ion here. So it is releasing the H plus ion. So this is conjugate. This is acid, and this is its conjugate base. Okay, so here in this concept we can see that ions can act as acid as well as base, which I have seen here. So this ion is acting as acid, this ion is acting as base. So ions can act as acid as well as base. Another example, if we say that water, that hydrochloric acid when react with water, we have Cl minus and H3O plus, and then this is acting as acid by giving the H plus ion, and this is acting as base by taking the H plus ion. So this is the conjugate acid base pair. These two are the conjugate acid base pair. Similarly, these two are the conjugate acid base pair. Similarly, ammonia, if we see that this is acting as base and it will take the H plus ion, so ammonium ion. So this is the conjugate acid base pair, and here in this this is the conjugate acid base pair. Okay. And this concept we can easily determine the strength of acids and base also by knowing the dissociation constant. So all these concepts are having limitations and advantages, their own limitations, so that we will cover in a while. Then coming to the Lewis concept, as per Lewis concept, base is a substance which is a proton donor, whereas acid is a substance which is a proton acceptor. For example, you are having a H plus ion, so this is electron pair deficient, so it is acting as Lewis acid, and Lewis base is the water pair is having the 2 lone pair, so it can donate the, so there is formation of coordinate bond. So Lewis acid is there, Lewis base is there, is electron donor, and Lewis acid is the electron pair acceptor. Here I have an example of ammonium and hydrogen ions. So this is Lewis base, this is Lewis acid because it is proton, this electron pair acceptor, and this is electron pair donor, so it is acting as Lewis base. Similarly, next we move here we have this is Lewis base, boron trifluoride is Lewis. So this is because you have to complete its octet, it requires an electron pair, so it will take fluoride ion and it will form the boron tetrafluoride ion. So similarly, aluminum chloride is acting as Lewis acid, and chloride ion is acting as Lewis base. So we have aluminum chloride. Okay, so this way acid is a substance which is a electron pair donor, is a acceptor, and then base is a substance which is electron pair donor. Electron pair donor is base, electron pair receptor is acid. Okay, let's see some of the example of Lewis acids. So H plus is Lewis acid, it can take to lone pair to complete this octet. Beryllium chloride, boron trichloride, aluminum trichloride, all these three are the Lewis acid because they can accept the electron pair to have the octet, to complete the octet around the central atom. So PCl5 again is a Lewis acid, it is having 10 electron pair around it, but as per the expansion of octet rule, it can take the chloride, another chloride ions to form the PCl5, PCl6 minus. Thus it is acting as Lewis acid. Then Fe2 plus, cobalt 3 plus, nickel, all these three are the Lewis acids. Why? Because we know that we have iron and cobalt and nickel. They're having atomic number 26, 27, 28, and near to it the state we will go that the inert gas is the krypton, that is having the 36 atomic number. So these three elements have tendency to have the configuration of the krypton. So here Fe2 plus, if we see that it is having Fe2 plus will have 24 electron, so it will require 12 more electron to have the 36. So it can take the lone pair from the 6 ammonium ions to form the coordinate compound, that is PNH2 6 2 plus. So here 2 plus is there, so here charge will be 2 plus. Similarly cobalt 3 plus again is having how much electron? Again it is having the 24 electron, cobalt 3 minus 3 plus, and then it can take again 12 electron pair to have the 30 configuration of the krypton element. Again nickel is having 28, so how much it is required to have the 36? It can have it by it requires 4 that is 8 more electron to have the configuration of krypton. So it can take 4 carbon monoxide molecules. So this is nickel, carbon dioxide tetra 4. So this way these three elements, that is Fe2 plus, cobalt 3 plus, nickel, these are acting as acids. So these are the acids, and these are acting as base because they are donating the electron pair, and their tendency is to have the configuration of the krypton to have the 36 electrons. Okay, so this we have seen the concept of acids and bases, and if you see some of the limitations of some of the limitations of each type of theory, here we can see that the first is limitation for any theory. So I told you that it is valid only for the aqueous solution. In non-aqueous solution, that will fail to explain the acidic or basic nature of the substance. It is the theory says that acids and bases are only acting in the aqueous solution, and also it fails to explain the acidic or basic nature of a substance that do not contain H plus or OH minus. For example, sulfur dioxide do not contain any H plus ion or OH minus, and carbon dioxide do not contain any H plus or OH minus. Sulfur dioxide do not contain any H plus or OH minus ion. Similarly here also ammonia also. So all these are acting as this is acid, carbon dioxide is acid, sulfur dioxide, ammonia is a base, so it is not having hydroxyl ion, so it is not able to explain why these are acting as acids or bases. This is a limitation. Then if you see the limitation of Bronsted-Lowry concept, this could not explain the acid which vary in aprotic solvents. So benzene is aprotic solvent, so it is not able to explain the concept because it is telling that acids or bases acting in aqueous solution only. There is no proton transfer reaction between the oxides, so sulfur dioxide, carbon dioxide, basic oxide like calcium oxide and magnesium oxides. So these are there is no transfer of H plus ion for the reaction between the oxides. So it is not able to explain that how these are acting as acids and bases. So it failed to explain this type of reaction. It also failed to exhibit the acid in nature. So how aluminum chloride is acting as acid, how boron trifold acting as acid when these two are not having the proton. This also, it is obviously it was not able to explain by the Bronsted-Lowry. Then if you see some of the limitations of the Lewis theory, that Lewis concept may or may not include the general idea of all coordination reaction, and so we've seen that in Lewis acid and Lewis base there is formation of coordination bond, but not always that coordinate bond is forming between the acids and bases. So this way it was not able to explain. It could not explain the behavior of proteinic acid like HCl and sulfuric acid, which do not form the coordination compounds with the bases. So these are not forming the coordination, but they are acid. So this concept could not explain how HCl and sulfuric acid is acting as acid. The Lewis could not explain the relative strength of acid. So we cannot determine the relative strength of acid and base using this concept. This concept was not applied to acid-base reactions. It could not explain the energy released during the covalent. Why energy releasing during the covalent bond? That also it was not able to explain. And we know that acids are acting are showing the catalytic activity also, but many Lewis acids do not exhibit the catalytic activity. And it also violates the octet rule, as we have seen that PCl5 is because of the expansion of a octet. We have PCl5 can have one more electron pair to have 12 electron pair around the central atom phosphorus. Okay, so this way we can see that this is acid and this is base, so it can take electron pair, and this it can donate the electron pair. So these are the limitations of lavish batch theory. Now these are 2 lines written which must be understood and to be explained with the help of examples. So all Arrhenius acids are Bronsted acids because both are giving the proton ion, while all Arrhenius bases are not Bronsted bases because one is Arrhenius is giving Arrhenius said that the mention of hydroxyl line, whereas Bronsted bases say that Bronsted bases are the proton acceptor. Okay, so this you have to give the example also. Another statement is justify the statement all Bronsted bases are Lewis bases, but all Bronsted acids are not Lewis acids. So this is also easy to explain. So all Bronsted bases are also Lewis bases, but all Bronsted acids are not Lewis acids. So this you have to explain these two with the help of examples that you can easily explain. Let us now see the concept of Ka and Kb. Ka and Kb is the dissociation constant for any acid, dissociation constant for any base, and these terms which are used to determine the relative strength of acids or bases. For example, we have acetic acid, it gives acetate ion plus hydroxyl ion because this is a weak acid, so it will dissociate to a very small extent. Whereas HCl is a strong acid, so it dissociates completely in the solution, giving H plus and Cl minus. So if we write the value of Ka for this reaction, we will have Ka equal to CH3 Cu minus, give you H plus ion CH3 COH. Okay, if you define the K for this reaction, it will be H plus Cl minus upon my HCl. Okay, so since this is a complete this is a strong electrolyte, so the concentration of the H plus and Cl minus will be higher in this case, and this is a weak acid, so concentration of acetate and the H plus ion is lower in this case. So we can say that the this K is very small, this K is strong. So this means that more K is there for any substance, more is acidic strength and less pK, and for a weak acid we will have the less Ka. So more is the Ka for acid, more is its strength, less is the Ka for the acid, lesser will be its strength, and pK is having just the opposite because pK is the minus logarithm of Ka, so it is the opposite to the behavior or the opposite to the trend of the Ka. So more Ka for acid, this means more strong is the acid, and more pK for the acid, this means weak is the acid. So less pK for the acid, so this means more strong is the acid. Okay, now let's see that how to compare the acid base strength. Some of the acids we can compare the acid and base strength. So if somebody asks you that among all the four, that hydrogen fluoride, hydrogen chloride, hydrogen bromide, or hydrogen, which is more acidic? So because iodine has more size, so it can easily give the H plus sign, so we will say that Hi is the more acidic one. So Hi, because it's having more, so if you see in the periodic table, we have fluorine, chlorine, bromine and iodine. Likewise, if you see here in this we have oxygen, and here we have nitrogen, and here we have the carbon. So in this way periodic table looks like this. So size is increasing in this way, and electronegativity is increasing in this way. Okay, so since iodine is having the largest size, so it can easily donate the hydrogen, and therefore it is more acidic than the HBr, then HCl, and then HF. Now if you compare the acid base strength of that HF, H2O, and H3, and this is which is the more acidic, so HF is more acidic compared to this. Why? Because fluorine is the more electronegative atom. It can snatch all the electrons from the hydrogen ends, thereby releasing it can donate the H plus ion very easily. So it is more acidic compared to H2O. Oxygen is less electronegative as compared to fluorine. Nitrogen is further less electronegative than iron, and carbon is the least electronegative element as compared among all the four. So CH4 is the least acidic. Now if we compare these acids, the acetic acid is there CCl. तो चलिए अब हम कुछ एसिड्स की जो स्ट्रेंथ है वो कंपेयर कर लेते हैं. तो लेट्स सी we have say 4 acids, HF, HCl, and HBr, and HA. If somebody asks which is the strongest acid among all these 4 acids, so I will say that HI is having the more acidic. Why? Because iodine is having, if you see in the periodic table, fluorine, chlorine, bromine, iodine, and here from top to bottom size is increasing, so iodine having the largest side, so it can donate the H plus ion very easily. So HI is more strong and HI is the least strong among the four acids which are shown, which are given. So in compare the acidic strength of HF, H2O and SH4. So here we can see that electronegative fluorine is the more electronegative and carbon is the least electronegative. So obviously if fluorine can take electron pair from the hydrogen atom and then easily give the hydrogen ion, so it is more acidic. Then comes the water, then comes the ammonia, and then comes the methane. Okay, so this way we can have such if arrangement is there for any acids, then we can have this rule. Then if we compare the acidic strength of acetic acid, then monochloro and then dichloro and trichloro acetic acid, so we will see that which is more acidic. So this will be more acidic compared to this. Why? Because here we can see that if it will go CH3 CO minus, if it will donate the hydrogen ion, so this will be the most stable one. Why? Because there are three electronegative atoms are there which can snatch the electron pair and making it more stable. So if we say here two chlorine atoms are there, here one single chlorine atom is there, here no chlorine atom is there, so no group is there attached to take the electron pair from it, making it stable. So this ion will be the most stable. So it can donate the hydrogen ion very easily. So this is the most acidic, and then this is the minimum acidic. Now if we compare HClO, HClO2, HClO3, HClO4, so here in this case we have the structure can be drawn like this. Here HOClO, then double bond O, double bond is double bond O. So if this is giving the H plus ion, so we will have the negative ion here, and this negative ion, because of resonance, there will be delocalization of this negative charge, and then this will be the most stable one. Since this is the most stable one, so this will be the more acidic one. So this is more acidic. Now if we compare the ammonium and the phosphine gas, so ammonium is more acidic. Why? Because this is having the small orbital and this phosphorus is having the long orbital, so it can easily donate the electron pair, it cannot donate the easily the electron pair. So ammonium is the strong base compared to the phosphine gas. Now if we compare the acid strength of fluoride and hydroxyl ion, ammonium ion and methane, that is methane ion, so we can see that if we compare this with this, we can see that the one which is the more acidic here, sorry, this is not, just see. So since this is more acidic, so this will be weak. This will be acidic strength of ion to compare, so this will be weak, and then the most acidic one will be methane, because this is least acidic, so it's conjugate so it base will be that is conjugate acid will be CH3. So it's is the acid, so conjugate base is fluoride, so this is conjugate base. So obviously if this will be more acidic and this will be the least acidic. तो अगर कोई एसिड है उसका अगर हम conjugate base निकालते हैं तो वो वीक होगा, और हेयर भी अगर इसका हम conjugate, क्योंकि ये वीक है और इसका हम conjugate base निकालते हैं तो वो एसिडिक होगा. तो इस तरह से हम जो है स्ट्रेंथ जो है एसिड बेस की हम कंपेयर कर सकते हैं अगर हमें कोई कंपाउंड दिए हुए हैं तो. और क्योंकि यहाँ पे डीलोकलाइजेशन में यहाँ लिख देता हूँ डीलोकलाइजेशन ऑफ द चार्ज. ओके, तो इस तरह से हम जो है एसिड बेस स्ट्रेंथ की जो है स्ट्रेंथ को हम कंपेयर कर सकते हैं. तो चलिए अब हम कंसेप्ट ऑफ पीएच और पीओएच भी देख लेते हैं. ये सिंपल सा कंसेप्ट है कि पीएच वी नो दैट द नेगेटिव logarithm of hydrogen ions, and we know that in aqueous solution H plus reacts with water to form the hydronium ions. So pH also can be defined as negative of the logarithm of hydronium ions, and we also know that at 25 degrees Celsius concentration of hydrogen ion is 10 power minus 7 molar, concentration of OH minus is 10 power minus 7 molar at 25 degrees Celsius in water. Now if we multiply both sides 10 seconds, then we have 10 minus 14, which is nothing but the ionic product of water. This is called the ionic product of water. and if we take negative logarithm on both sides, we can easily derive pH plus pOH is equal to 14. pH plus pOH is equal to 14. Now let's say some of the examples. We want to calculate 10 power minus 3 molar HCl pH of 10 power minus 3 molar HCl. Now HCl in water giving using the hydronium and chloride. Similarly, water can itself can act as acid and basis, I have told you. So there is a exchange of hydrogen ions which is happening between the water molecules also. So there will be a hydronium ion and there is a hydroxyl ion. Okay, now here if we see that the concentration is 10 power minus 7 molar, 10 power minus 7, we know that here it is given that 10 power minus 7 10 power minus 3 molar is HCl. So here hydronium concentration will be 10 power minus 3 molar. Now this hydronium ion should be added with this hydronium, but if you see that 10 power minus 3 is very large as compared to 10 power minus 7, so this can be ignored. So if this can be ignored, then pH of 10 power minus 3 molar HCl will be equal to minus logarithm 10 minus 3, that is equal to 3. Now if it is that is asked for 10 power minus 4, it will be 4. 10 power minus 5, it will be 5. 10 power minus 6, it will be 6. Now if somebody asks you to calculate the pH of 10 power minus 7 molar HCl, then obviously if 10 power minus 7 is same as 10 power minus 7, so here in this case we cannot ignore 10 power minus 7, so it equal to 2 into 10 power minus 7, and if you put it in the formula, it will be 7 minus log 2, and which is 7 minus 0.3010, that is 0.6990. Now if we calculate the pH of 10 power minus 8 molar HCl, so here this added to 10 power minus 7 because this is smaller, 10 power minus 8 smaller than 10 power minus 7, so it will equal to 1.1 into 10 power minus 7, and pH will be equal to 7 minus log of 1.1, which is around 6.9. Okay, so this way we can see, we have to first see whether the concentration which is given of the acid is near to 10 power minus 7 or not. If it is near to 10 power minus 7, then we obviously the concentration of hydronium, or the contribution of hydronium is coming from the water, that also to be accounted for. Okay, now another question is how you will calculate the pH of 10 power minus 3 molar acetic acid solution, because this is a weak acid, so I also require the degree of dissociation, say 10%. So at equilibrium we will have C minus C alpha of acetic acid, C alpha of acetate, and C alpha of the hydronium ions. Okay, now if the concentration is given as 10 power minus 3, so degree of dissociation is 10%, so C alpha, that will equal to 10 power minus 3 into 10 power minus 1, that is equal to the 10 power minus 4 molar, pH equal to 4. Now if instead of giving a degree of dissociation, they can also give you the equilibrium constant, or that is the dissociation constant for acid, that is equal, here it is given 10 power minus 5, here it is the concentration is 10 power minus 3. So you know that alpha is equal to A by C. This is nothing but the Ostwald dilution law, and if you put the value of if you want to calculate C alpha, because you have to calculate the C alpha, then C alpha will be equal to A C. Okay, now K is given as 10 power minus 5, and then C is given as 10 power minus 3. So if you multiply, you will have 10 power minus 8 and square root of the 10 power minus 3 minus 4, and then pH will be equal to 4. So in this way they can either give you for weak acid, they can either give degree of dissociation, or they can either give the value of Ka, and accordingly you can calculate the pH. Okay, and now some of the important points about water, that mass of 1 liter of water is around 997, that is around 1000 gram it is, and molar concentration of water is 55.5 gram mole per liter, and this you know how it is coming. So we know that it is the weight in gram, that is 1000 divided by, so we are calculating for 1000 gram, 1000 divided by 18, that is the molecular weight of water. So this will come to 55.5 gram mole per liter, and the number of water molecule in 1 liter, obviously that Avogadro number is 0.023 into 10 power 23, that is 3.34 into 10 power 20. Now concentration of H plus ion in 1 liter of water will be equal to 10 power minus 7 mole per liter, and concentration of hydroxyl ion in 1 liter of neutral water, that will equal to 10 power minus 7 mole per liter, that have to be 25 degrees Celsius. Now number of H plus ion in 1 liter of water, obviously you have to multiply the Avogadro number, that is 6.023 into 10 power 23, and it will come to 6.023 into 10 power 16, and hydroxyl ion, the number of hydroxyl ion will be the same as number of hydrogen ions, so it will equal to 6.023 into 10 power 16. Now I want to calculate dissociation constant, or degree of dissociation for pure water. So here alpha will be equal to number of moles dissociated, that is 10 power minus we know that H plus n, and total number of moles initially taken, that is 55. So it was initially how much, 55 1.5. So degree of dissociation is 1.8 into 10 power minus 7 percentage. So very small dissociation is there for the water in the very small dissociation, that is very small dissociation. So water dissociate to very small extent, that is 1.8 into 10 power minus 7%. So out of total 5.5 moles of water, only 1.8 into 10 power minus 7% is getting dissociated. Okay, so this is the general basic about the water. Let us now start the concept of salt hydrolysis. So क्वेश्चन इन दस, अगर मैंने एसिड को पानी में डाला तो सोल्यूशन एसिडिक हो जाता है, बेस को पानी में डाला तो सोल्यूशन बेसिक हो जाता है। अगर मैं साल्ट को पानी में डालूंगा तो सोल्यूशन कैसा होगा, वो डिपेंड करेगा कि वो साल्ट जो है किस टाइप के एसिड या किस टाइप के बेस से बना हुआ है। तो हमारे पास 4 केसेस हो सकते हैं। अगर हमारे पास स्ट्रॉन्ग एसिड और स्ट्रॉन्ग बेस से हमारा कोई साल्ट बना हुआ है, जैसे NaCl है, तो उसका जो सोल्यूशन पानी में होगा वो न्यूट्रल होगा। अगर कोई साल्ट हमारा स्ट्रॉन्ग एसिड और वीक बेस से बना हुआ है, जैसे अमोनियम क्लोराइड है, तो ऑब्वियसली वो एसिडिक होगा, क्योंकि जो Cl है वो हमारा स्ट्रॉन्ग एसिड से आया है, तो इसलिए स्ट्रॉन्ग एसिड का कंट्रीब्यूशन ज़्यादा हो जाएगा, तो वो एसिडिक हो जाएगा। अभी हम इसको डिराइव भी करेंगे। उस तरह से अगर हमारे पास जो साल्ट अगर वीक एसिड स्ट्रॉन्ग बेस का, तो ऑब्वियसली वो बेसिक होगा साल्ट, और अगर सोल्यूशन जो बनेगा वो बेसिक बनेगा। बेसिक एसिड और वीक बेस का साल्ट है, तो डिपेंड करेगा कि पीके और पीकेबी की वैल्यू क्या है। तो अगर पीके इक्वल होगा तो सोल्यूशन न्यूट्रल होगा, पीके अगर पीकेबी से ज़्यादा होगा तो सोल्यूशन बेसिक होगा, अगर पीके लेस देन पीकेबी होगा तो एसिडिक होगा। तो ये जनरली जो है न्यूट्रल, ऑलमोस्ट न्यूट्रल होता है। लेकिन if pK value and pK value is if we compare the pK and pKb value, then accordingly we can arrive at whether the solution will be neutral or basic. That we'll see in the coming lecture. That if pK equal to pKb, then this will be neutral. pK is greater than pKb, it will be basic. pK is less than pKb, it is acidic. Now what is happening is that first, whenever a salt is dissolved in water, then first is ionization which is happening. So here it is ionization, and then there is happening the hydrolysis, second hydrolysis. Okay, now this is ammonium chloride is there. This is a salt of weak base and strong acid, so it get ionized to ammonium ion and the chloride ions. And this chloride ion is weak because it is coming from the strong acid, so this will weak, this won't get hydrolyzed. Only ammonium ion will get hydrolyzed, and then we'll have ammonium hydroxide and H plus ion. And since the H plus ion is released, and that is why the solution has become acidic. Okay, so pH here is less than 7. Now take a case of strong weak acid and strong base. So strong base is coming, so the solution will be basic, and then first will be ionization, as shown. The first reaction will be ionization, second will be hydrolysis. Okay, so in ionization we have acetate ion and sodium ion, and this acetate ion which is produced will again get hydrolyzed. First it will be hydrolyzed to acetic acid, then OH minus. Since OH minus is a relation, so solution is basic. This NH won't get hydrolyzed because this is weak, this is coming from the strong base. Okay, so the solution will be basic. Now take the concept of NaCl, because NaCl gives first Na plus and Cl minus, and since these both are weak, so they can not hydrolysis. So if somebody asks you that which type of salt is not getting hydrolyzed, it's the salt of strong acid and strong base which is not getting hydrolyzed, because the ions which are produced are weak, they are inert, they are not getting hydrolyzed. Okay, and then take the concept of weak acid and weak acid. So weak acid and weak base, so it is giving you acetate and the ammonium ions, and this again, when both of the ions will get hydrolyzed, we'll have the acetic acid and NH4H. And obviously whether the solution is acidic or basic, it will depend on the value of the pK and pKb that we will see in a while. Okay, so if both are shown here, that if both are equal, then the solution will be neutral, and pK is more than pKb, then it's basic, and pK is less than pKb, then it is acidic. So this we will try it. Okay, now if we want to acidify, say, some compound, if somebody asks you to identify whether it will be acidic or basic or neutral, some salt is there and some salt will be given to you, you will have to identify whether it is acidic or basic or neutral. Now if you see the sodium acid, so it is coming from strong base, so it will be basic. Aluminum chloride is coming from strong acid, so that means strong acid and weak base is there, so it will be acidic. Copper sulfate, acidic. Sodium bicarbonate, this is basic, because this is NaOH is coming from the strong base. KCl, it will be acidic, okay, because it is coming from so KCl is there, so it will be neutral. Why? Because it is coming from strong acid and strong base. QH is strong base, strong HCl is also a strong acid, so it is a neutral. And this is coming for weak acid and strong base, so basic. So this is for a strong acid, acidic. This is acidic, this is acidic. So we can identify whether salt is acidic or basic depending upon whether it is a strong acid or strong base. Identifying whether the type of acid or base which is involved in preparation of the salt, we can identify whether the salt solution will be acidic or basic or neutral. Okay, now we have to drive. The question is, you have to drive the pH of this salt solution that is formed from strong acid, strong base, strong acid, weak base. All the four we have seen that we can understand. That is for strong acid, strong base. What is with the pH of solution of salt formed from strong acid and strong base in water? Then we have strong acid and weak base, weak acid and strong base, and weak acid and weak base. So we have to drive the pH. We have to prove that for strong acid and strong bases, that what will be the pH. Obviously we cannot drive it by this method because here hydrolysis won't happen, and here pH, how you have to prove that pH is less than 7 in this case, pH is greater than 7 in this case, and then here it depends on pK, PV, that we will drive. Now first take the example of sodium acetate. It is coming from the strong base and weak acid. So first ionization will happen as shown here. First ionization will happen, then the hydrolysis will happen like this. And if the initial concentration is C, and then after equilibrium we will have C minus C alpha of acetate ion and C alpha and C alpha of the hydroxyl ion. So fraction of what is this? Alpha is the degree of hydrolysis. So here alpha is not degree of dissociation, it's degree of hydrolysis. That is fraction of the salt which is getting hydrolyzed. How much fraction of the salt which is getting hydrolyzed? And this is very, very small. Okay, now if you write the KH value for this will be this, that's acetate ion, and this is acetic acid, hydroxyl ion, and then acetate ion. Okay, now this is nothing but equal to this will be equal to Kw by Ka. We can easily derive it also, because Kw is H plus OH minus K is K for this acid will be CH3CO minus H plus, and that for this reaction, if we have to consider this reaction for this. So K for this value will be equal to CH3CO minus H plus divided by acetic acid. So this H plus will go, then this will equal to KH. So KH equal to Kw by Ka. So for strong acid and weak base, we will have KH equal to Kb. Similarly, and weak acid, weak base, we have KH equal to Kw by Kb. And if you want to calculate alpha, alpha is for weak acid and strong base, it is dependent on concentration of the salt, and weak acid, strong acid, weak base, the degree of dissociation again dependent on the concentration of the salt. But for weak acid and weak base, the degree of dissociation is independent on the concentration of the salt. So here no concentration term is coming. Okay, so from these two equations, this will help. The value of KH and alpha will help to calculate the pH of the salt solution. So let's see how to calculate it. Say we have the example of here, we have derived here that the degree of dissociation, degree of hydrolysis of salt, degree of hydrolysis of a salt of weak acid and weak base is independent of the concentration of the salt. So it is not dependent on the, so there is no, how will you prove it? So this is a weak acid, is the salt of weak acid and weak base, and then first the ionization will happen, and then hydrolysis will happen. Okay, now if we calculate the Ka, that will be the C alpha, C square alpha square divided by C square alpha minus alpha square. So C square will go, alpha is very, very small, so this can be neglected. So alpha equal to root KHC. So it is independent of the concentration of the salt. That is, the degree of hydrolysis is independent of the concentration of the salt. Whereas for strong acid and weak base, or salt of strong acid and weak base, and also salt of weak acid and strong base, the degree of hydrolysis is dependent on the concentration of the salt. But here in this, it is independent of the concentration of the salt. Okay, now we will derive the pH. So first case is strong acid and strong base. We know that there will be no hydrolysis, because the ions which are produced by strong acid and strong base, the salt of the strong acid and strong base will be weak, so they do not participate in the hydrolysis, as I will already told you. Now to see the case of strong acid and weak base, we have ammonium chloride. It will give ammonium ion and chloride ions, and the ammonia, this chloride ion won't get hydrolyzed, so ammonia will get hydrolyzed with form ammonium hydroxide and hydrogen ion. And here we have already seen that alpha will be KH by C and KH equal to Kw by Kb. So that is alpha is equal to Kw by Kbc. Okay, so here alpha is equal to Kh by C. So if you put the value of Kh here, so Kw by Kbc, and here H plus, if you see the concentration of H plus is C alpha, so if you put the value of alpha here like this, it will be equal to Kw C divided by Kb root of this, and if you take a negative logarithm of this, negative logarithm of hydrogen ion minus half, that is log Kw plus log C plus pKb, and this way if you rearrange it, the pH equal to 7 minus half of log C plus pKb, so something that is subtracted from 7, so the pH is less than 7, that is, it means the solution is acidic. So we have proved that the salt of strong acid and weak base will be acidic in nature. This you have to put, this we have proved, that is pH of the salt when dissolved in water will be less than 7 for a salt which is made up from the strong acid and weak base. Okay, now see the second case, which is weak acid and strong base. So obviously it will be basic. So H minus is ion releasing, alpha value Kh by C, and Kh equal to Kw by Ka, and OH minus, here OH minus will be C alpha. So here KHC C and Kh value we have put it here like this, and then we have taken logarithm on both sides. So pH is coming as 7 minus half log C plus pK, and then pH will be equal to, since we know that pH plus pOH is equal to 14, so therefore pH equal to 7 plus half, pH is greater than 7, so the solution will be basic. So hence we have proved that when a salt of weak acid and strong base is dissolved in water, then the solution will be basic and pH will be greater than 7, so hence we have proved it. Okay, now we see the case of weak acid and weak base. So here as ammonium acetate is an example of a salt which is formed from weak acid and weak base. So here both will be get ionized. So here ionization, first step will be ionization, and both will be get hydrolyzing. So in this case both, because both are strong, so in this both will get hydrolyzed to acetic acid and ammonium 4H. So alpha is equal to root of Kh, we have already seen, independent of the concentration, and Kh equal to Kw by Kb, that also we have seen. Okay, now K for this reaction will be equal to acetate ion and H plus and C acetic acid, and H plus will be equal to Kn K C acetic acid upon acetate ion, and then if you put the value of concentration, then here it will go C alpha and C1 minus alpha, and C will go here 1 minus alpha will also go, K equal to alpha, and root of Kh we can write, and K into this, and this can be written as this. Taking negative logarithm of this, we will have like this, and then pH equal to 7 plus half pK minus pKb, and obviously if pK is greater than pKb, then obviously this will be a positive number, and then the solution is pH is greater than 7, so basic, and pK is less than pKb, pK is less than, so this will be a negative number, and this 7 minus something subtracted something, that will be pH is less than 7, so acidic, and then if both are equal to, then pH will be equal to 7, because pK minus pB equal to 0, so pH will be equal to 7, that is solution is neutral. So hence we have proved that depending on the types of salt, we can have the acidic, basic or neutral solution, and even in the case of for strong acid and strong base salt, no hydrolysis is happening, and if for a solution of salt of made up from strong acid and weak base, we having the solution in water as acidic, and for a salt from weak acid and strong base, we have the solution pH of the solution as greater than 7, that is basic, and for a salt coming from weak acid and weak base, it depends on the value of pK and pKb whether the solution will be acidic, basic or neutral. That we have proved it, and we have derived the pH also. Okay, it's very simple to derive, and these are asked also.